Next speaker, Mihir Pant.
Hi, thank you so much. So I'll be talking about in my talk today a trick called dynamic bias arrangement that we use in our architecture, in our physical system, which is photonics. And it's a trick which has led to a significant increase in error tolerance in our physical system. And we hope that it can help other physical systems as well. So this is the paper that I'll be talking about. I'd like to thank my co-authors, Hector Bombin, Chris Dawson, Naomi Nickerson, and Jordan Sullivan. And today I'd like to also thank Daniel for providing the laptop for this talk. Otherwise, my laptop was not able to be plugged in. So thank you so much for that. Otherwise, it wouldn't have worked. So thank you so much. We've heard already many times in this conference that many physical systems have a bias in errors. For instance, throughout this week, we've heard of platforms where errors are mainly Z errors, or we've heard of talks on biased erasure. And one big question is, how can we take advantage of biased noise in these physical systems? So there are two kinds of protocols which actually one can try to take care of biased noise. So one is what we call static protocols. So what has been discussed in Alex's talk just now, in Shruti's talk, which was there on Tuesday, are a class of protocols which we call static protocols. And the trick there is that you know that I can bias my entangling gate in two ways, where I take either more phase flips or I take more bit flips. And before runtime, I structure my operations in such a way such that I take advantage of the kind of bias that I have in the noise. So these are all static protocols. And actually, as you saw in Alex's talk, these ideas are very good, and you get a great boost in the threshold when you play these games. In this talk, I'll be talking about a slightly different class of protocols, which I will be calling dynamic protocols. And the difference here is that rather than choosing your operations before runtime, you choose your operations during runtime instead. And the reason why we want to do this is that we find that you get a lot more error tolerance when you play this game. And it works for more moderate values of bias as well. Although like these games of static protocols, they work well when you have a very large amount of bias. If you have a more moderate value of bias, the game sort of struggles, and I'll be talking a little bit about that as well. In particular, in our physical system, we find that this leads to 3 times more tolerance to photon loss. And importantly, we can do this with the same operations that we use in static protocols. The overhead that we play is that we need more classical logic to make this happen. But it's only classical logic. Of course, that's still hard, but it's still easier than actually doing some new quantum operation. This is an outline of my talk. I'll be talking about photonic quantum computing, which is the platform that we work with at PsiQuantum. I'll be talking about why it's a nice platform for quantum computing, but then I'll also talk about why it's a weird platform for quantum computing. So there are certain idiosyncrasies that photonics has, but thankfully, the weirdness of photonic quantum computing can be solved by certain theoretical tricks, which includes dynamic bias arrangement, which is what I'll be talking about today. So the reason why we like photonics is that fault tolerance will be required for commercial applications. So this is a case that you need to make in other conferences, but hopefully I don't have to make that case in this crowd here. We know that fault tolerance will require a very big quantum computer. So despite all the sort of improvements that we've seen on the overheads, it's still true that for any large-scale application, you will need a very large number of devices in a quantum computer. And photonics, we believe, is a great platform for making a very big quantum computer. And that's because it's easy to make a large number of devices it's easy to make a large number of photonic devices because of the trillions of dollars of investment that has gone into semiconductor fabrication over decades. So photonics is used in all sorts of communication and computation applications in classical communication, and that's why we can leverage off this maturity. So instead of actually fabricating our devices in a lab, we can instead, no thanks. can see. Yeah, so as I was saying, we can leverage the maturity of semiconductor fabrication. And the good thing is that instead of having to fabricate all the numerous devices that we will need in a lab, we can instead send our designs to a multi-billion-dollar fab, and they ship us back these nice silicon wafers which have very nice devices on them. The qubit that I will be talking about in this talk is a dual rail photonic qubit. Again, I think Alex has already given a very nice introduction to dual rail qubits. We inherit many of the good properties of dual rail qubits. So we have our qubit is one photon in two modes. If the photon is on the top rail, we call it a logical 0. If it's in the bottom rail, we call it a logical 1, and that's basically it. That's our physical qubit, I suppose. So we have high fidelity operations in this platform. We have scalable fabrication. The dominant error mechanism is loss, which leads to erasure, which is the same sort of advantage that we talked about in previous talks. And one special advantage that we have in photonics is that we have easy transport. So although there are many platforms for quantum computation which each have their own advantages, for communication, it is quite clear that photonics has a unique advantage, so that allows us to connect our modules in a very easy manner and do all sorts of weird things with. It's easy to transport our qubits because they're photons. Cool. So now I'll just touch, these are all the good parts which you would expect a person from PsiQuantum to talk about, but now I'll talk about the weirdness of photonics as well. So one of the problems that we have in photonics is that we have a completely different set of fundamental operations. So for regular quantum computation, in most platforms, you think of a set of primitive operations which consists of non-destructive entangling gates. Like the C0 gate, you think of single qubit rotations and you think of single qubit measurements as being your primitive operations. In photonics, unfortunately, we don't have a non-destructive entangling gate. So instead, our primitives look something like the picture that you see on the right here. You have resource states, which are small, constant-sized entangled states, of which the size is independent of the size of the computation. And every circle that you see here, oh man. Oh, it worked. Sorry about that. Every qubit that you see on the figure on your right is a qubit. Every circle is a qubit. And this is basically an example of a graph state. And the orange circle that you see here is a fusion, which is a destructive and probabilistic entangling measurement. So a typical example of a fusion is a measurement that performs a Bell basis measurement. So it measures XX and ZZ on the two input qubits that you see here. And unfortunately, this is a destructive measurement that the qubits that go into the fusion are actually destroyed after the measurement is performed. So the first problem that we have is that entangling operations are destructive. For this, our solution is a slightly different paradigm for quantum computation that we call fusion-based quantum computation, and the basic idea is that if you take these resource states and fusions and you put them in some sort of 3D arrangement, you can actually get a kind of fault tolerance which is very similar to surface code fault tolerance. So again, you can see states here. The hexagons that you have are our resource states. The orange circles that you have are our fusions. Every measurement from every fusion here produces 2 bits of information, which are the XX outcomes and the ZZ outcomes. And what you end up with is a fault tolerance structure, which we are all familiar with. It's a syndrome graph. So every measurement here in the syndrome graph is represented by one edge. Every bit that we get from a fusion represents one edge in the syndrome graph. As is the case with surface code fault tolerance, we end up with 2 disconnected graphs, which we call the primal syndrome graph and the dual syndrome graph. And the circles here represent checks. So there is some inherent redundancy in our stabilizer measurements in the picture on your left. And that's basically what allows us, what gives us this sort of syndrome graph structure that you see here. So for every fusion, one outcome goes to the primal and one outcome goes to the dual. And so this is one of the problems that we face. just one thing I'd like to say here is that this the syndrome graph that you see here is a 3D structure, right? And so it's very hard to visualize the whole structure. So that's why I've made a bit of a cartoon for this 3D structure. But actually, it's a pretty complicated structure. So in addition, the second problem that we have in photonics is that we have probabilistic entangling gates. So let's say you perform a fusion, and I have, as I said, you have one XX outcome and one ZZ outcome. Let's say the XX outcome goes to the primal, the ZZ goes to the dual. You're measuring 2 bits of information. Even if we have perfect components in photonics, we have a baseline biased erasure rate of 50% in photonics. So even if all our measurements even if all our components were perfect, half the time I will lose either the primal outcome or the dual outcome, which off the bat seems very serious. So if we were not smart about this, it says that we end up with a baseline average erasure probability of 25%, even with perfect components. This is potentially a big problem. And in addition, we have unbiased erasure that loss adds as well. So the good thing here is that the erasure is actually biased and reconfigurable. That's sort of the saving grace here. What that means is I can perform my fusion in 2 ways. So let's call this a fusion type A and a fusion type B. If I perform a type A fusion, my primal erasure is going to be much greater than my dual erasure by some fraction alpha. So basically, if I perform a fusion type A, I can protect my dual and I risk my primal. Instead, if I perform a fusion type B, I'll have a lot more dual erasure and my primal is protected. So depending on what I want to protect, I can perform either a fusion type A or a fusion type B. Alpha is some constant greater than 1, but a typical value of alpha for us is around 5. That's the sort of bias we see in our operations. And this is sort of the FBQC analog of bias preserving gates. So yeah, this is the problem. There's lots of erasure, but thankfully it's biased. We of course need to be able to switch between fusion type A and type B, and this fusion choice can be made with the switch in photonics, which is a component that is easy to fabricate. So I just like to point out that these are the same sort of operations that you use in static bias arrangement. So the fundamental operations are the same. The only difference is in static bias arrangement, the switch settings are predetermined, whereas in dynamic, you decide during the protocol. There are some details I won't have time to go into here. There are some trade-offs between the amount of biased and unbiased erasure that you can actually make in this physical system. So there is actually a bit of a mapping that happens between how loss maps to unbiased erasure and so on. But I won't go through that. The paper has all those details. And the basic game we're going to play is that, yeah, let's say if we do fusion A, primal is unhappy, dual is happy. If we do fusion B, primal is happy, dual is unhappy, and we just need to figure out, the game we're going to play is who do we want to make happy at what point of time is the basic game that we're going to play. Cool. This thing, so now I'll get to the actual trick of bias arrangement. A disclaimer, since we are a photonic quantum computing company, we've set up our problem in a way that works for us. So I'll be talking about dynamic bias arrangement in a photonic system with loss and erasures, but it could be applied to other sort of platforms as well, which have more Pauli errors. But although there have been a lot of talks about erasures already, so maybe it is well motivated already. So the first idea we tried was static bias arrangement, which is an idea similar to what we saw in Shruti Puri's talk and we saw in Daniel's talk as well. We saw in Alex's talk as well. The idea here is that we know that there are two kinds. The syndrome graph itself is a 3D structure, which has edges. Actually, it's not. There are edges which go between the planes as well here. So what you do is the syndrome graph that you obtain in a typical setting is in the space-time picture. It is a 3D structure. What you do is that you arrange the error-prone measurements in such a manner that they form disconnected 2D planes. That's the basic idea that you play with in static bias arrangement. We know that it's actually, one way to view this is that it's harder to percolate in 2D planes as opposed to in a 3D structure. And therefore, we have better confinement of our errors. And therefore, what we find is that this sort of 2D confinement works very well and gives us a big jump in our threshold if the bias is very high. Unfortunately, what we found is that this trick sort of works well only if the bias alpha is much, much greater than 1. As long as we start adding unbiased erasure to this system, what we find is that we start connecting these planes is the problem. And so this sort of, since our game is dependent on this game of dimensionality reduction, we find that very quickly as we add unbiased erasures, they sort of, the planes start getting connected, and that sort of gives us a hit in our threshold. And with this particular game, we find that we end up with less than 0.5% of loss tolerance per photon if we play this game. However, so now how can we resolve the situation? That's when we introduce dynamic bias arrangement. So rather than predetermining what has happened, the idea behind dynamic bias arrangement is we try to decide the bias for future fusions based on what has happened in the past. That's the basic idea. And the second principle is that we try to redistribute errors in a way which is less likely to cause a logical error. So as you are probably already familiar, not all errors are equally bad. So depending on what kind of arrangement you have of your errors, an error can be really good or really bad. So if you look at the left, if I take a particular syndrome graph, if I have a long chain of connected erasures, that is really bad. So the black in this figure represents erasures. The green represents measurements which are not erased. So if you have a situation on the left, that's really bad. But if you take the same number of erasures, but you organize them in a manner that you see on the right here, it's not as bad. So isolated erasures are actually not so bad. Just one thing I'd like to say is that the actual syndrome graph that we worked with is very complicated. So to make life simpler, I'll be explaining the trick with a simpler syndrome graph. I'll be explaining the trick with a simple square syndrome graph, where we'll have two syndrome graphs. We'll have a primal and a dual, there'll be some measurements there'll be a measurement in the primal which is coupled to a measurement in the dual because they are from the same fusion. And that's where we can make the trade-off, essentially. So the decision that I need to make at any point of time is that at any point I would have measured some number of qubits. So I'll have some measurements that have happened in the past. That is the white region that you see here. And there's a gray, for which I do have information of what has happened. And there's a region in the future that I don't know what's going to happen. And at any point, I need to figure out, based on the information that I do have, I need to figure out where would I rather have errors. Would I rather have errors in the primal, or would I rather have errors in the dual? That's the basic game I'm going to play. And so let's look at one example of this. So in this figure, I have the primal and the dual. The green lines are basically measurements that you see which have been performed successfully, so I know their outcome. The black lines are erasures that have happened in the past. And the dotted lines, the dotted blue and red lines that you see here, are measurements for which I don't yet know what is going to happen. So if I'm in this sort of position, what should I do? Should I try to protect A or should I try to protect B? So let's say A and B here are the two measurements which come from the same fusion. In this situation, it turns out my decision is easy. A is essentially useless. It's better to protect B. So if you have any measurement, if you have any edge in the syndrome graph that is connected by a path composed of erasures already, then we sort of know that measurement is useless. I can basically totally bias my measurement in such a manner, just try to protect B as much as possible. It's an easy decision. However, not all my decisions are always going to be easy. There'll be certain situations where neither edge is totally useless. So let's consider this situation instead, where I have a measurement A and a measurement B. And now in this particular scenario, both of them could potentially help me. So now what do I do? In this case, we use a heuristic, which is actually inspired by explosive percolation theory. And the heuristic is quite simple. The basic idea behind the heuristic is we basically try to avoid errors in edges that are going to connect large clusters of erasures. So we define a cluster as a set of nodes connected by erasures, and we define cluster exposure as the number of edges that can grow in a cluster. So it's not exactly the size of the cluster. So especially in a scenario where we rarely care about erasure, measured clusters are relatively benign. So if you consider the sort of cluster that you see on the bottom left here, it's a big cluster, but it's surrounded by measurements that have already been successful. So it's relatively benign, so it'll have a small exposure. So we define this quantity called exposure, and we define this quantity called exposure, which essentially tells you how bad each erasure cluster is, and we define an edge exposure, which is the product of the neighboring cluster exposures, and that basically tells us how important an edge is. And the heuristic is simple: just protect edges or measurements which have a higher exposure. That's the simple thing. Why did we choose product? Why didn't we choose the sum? We actually, again, from explosive percolation theory, they found that product is better than sum. It worked better for us as well. That's why we use product. There are, of course, this is a a simple example. There are certain modifications that when you add Pauli errors. So in this case, for instance, I don't, my exposure is only counted by the number of, by the size of the cluster that can actually grow in the future. However, in the case of when you add Pauli errors to this game, you'll have a situation where even things which have been measured in the past might not be perfect. So there are certain modifications that you make when you actually are considering Pauli errors that are described in the paper. One important consideration, of course, is that you need efficient algorithms because you need to compute this fast. And so we have that described in the paper as well. So now let's consider a numerical example. Let's take the same fusion network that we considered previously. Again, I think this trick in general works for many different fusion networks. I'm actually, in my talk, I'm sort of sticking to the simplest one just for pedagogical reasons, but you can use it in any physical system. And again, so for every fusion, we have the following problems. We have three sources of errors here. We have a baseline biased erasure, which just comes from the weirdness of photonics. On top of that, we have every photon is lost with probability L, which is our unbiased erasure. And in addition, we are also going to, our error model is going to include a situation where every bit from every fusion is incorrect with some probability. Let's call it PM. So now if we consider things, this is what we consider, we obtain this particular threshold surface. So this threshold surface essentially tells us what's the maximum amount of error that a particular scheme can tolerate. Or so on the x-axis, you have the loss probability L. On the y-axis, you have the error probability PM. And the blue region here encloses the area of PM and L, where I can actually where I'm below threshold, and I can actually successfully correct for both loss and error probability simultaneously. So the blue region here is already a good scheme which accounts for and takes advantage of many of the tricks that Alex and Shruti talked about. And with this scheme, we get a better error tolerance than we would have without any bias arrangement, but it's still sort of limited. And what we find is that if we use dynamic bias arrangement, we end up with this orange line that you see here. We are able to expand the region of operation here significantly. And so for all values of loss and error probability, we find that we get a better threshold. One thing which you might notice here is that there's a little bump in the curve that you see here. That's because we optimized our protocol to operate in this particular region, and that's why we are operating a bump there. If people were interested in other regimes of operation, it might be possible to, like sort of, there are some hyperparameters in our simulations. It might be possible to play with that and get something which like goes in a straight line. But in our region of operation, which is close to the x-axis that you see here, we get 3 times the loss tolerance as static biased arrangement. One thing I'd like to mention is that, again, this is just one example of an architecture that I presented. This is the one that is closest to surface code, but you could try it with another architecture. So just in the paper, we just took one more example of an architecture, and in that, we also got a similar close to 3x improvement. Our loss tolerance in another example went up from 2.7% to 7.5%. And one interesting thing in this case was that in this particular example, the bias in our physical operations is only 4.4:1. So it's not a lot of bias that we are actually playing with. I'd just like to also mention that it's actually compatible with other work as well. So this is, bias arrangement is one particular knob that you can tune to play with this. It's compatible with, there have been many other works which have talked about different fusion networks and different kinds of encoded fusions, which you can use in conjunction with the trick that we are describing here. In particular, I'd like to point out a recent paper that we had from our company, which talks about something we call fusion complexes. And it's an automated search for fusion networks, essentially, which yields, in the paper, it yielded 627 different fusion networks. And this trick can work for all of them if you wanted to. So, yeah, general. So I, of course, talked only about photonic architectures, which are heavy in erasures. What if you had other architectures which had Pauli errors? Of course, what we expect is that you can actually play a similar game in other situations as well. You can, the thing that we will have to do if you want to adapt it to other architectures is we'll have to redefine what we mean by exposure. So instead of inferring how bad an edge is based on some sort of configuration of erasures, we can probably play some trick where we try to infer how bad a particular cluster is based on some configuration of syndrome. So that's sort of for future work, but that's a sort of game that we can also play. Finally, I'd like to say that in this talk, I've talked about a very simplified error model where we had 3 sources of error: biased erasure, unbiased erasure, and Pauli error. But in reality, things are a lot more complicated. In our talks, we like to present things in a simple manner, but the bulk of our company actually spends time figuring out how to make these tricks work with a more complicated error model. So the tricks that I've described here work with a more complicated error model and a full stack simulation that we do in our company, which takes actual hardware errors like photon distinguishability and switch loss and beam splitter loss and all sorts of dispersion in the fiber and whatnot, and takes all these more than 25 sources of errors, maps it all the way from components to circuits to resource state generation to fusion networks, all the way to logical gates. And the tricks that I'm describing here actually work through when you actually map it through all these, this full stack as well. So yeah, thank you. In conclusion, I guess I've just talked about photonics. It's an attractive platform for scalability, but it has a weird error model. Thankfully, theoretical tricks can be used to actually handle this weirdness. And in particular, today I've described a trick called dynamic bias arrangement, which allows us to increase the loss tolerance in a photonic architecture by 3 times compared to static bias arrangement with the same sort of quantum resources. The same trick can be applied to any fault tolerance scheme with a syndrome graph and multiple bias options. So this might be useful for tolerating more errors in other physical platforms, I hope. And furthermore, you could actually maybe generalize the tricks here even further. So firstly, all the tricks here are essentially heuristics. They're inspired by some percolation theory. But there's no reason to believe that these are optimal. We might be able to play more games and come up with a better heuristic or maybe an optimal solution if we play different games. And furthermore, since there's so much talk, the trick here doesn't have to be limited to syndrome graphs. We could further generalize it to other classes of codes, to work with Tanner graphs, which are useful when we talk about LDPC codes, for example. So yeah, there's plenty of room for improvement here as well. This is the paper. Thank you so much. That's all.
Question from here over there.
Hiya, thanks for the talk. I've just got a question about the requirements on the switching. So how quick does the feedback loop have to be between making the decision of changing the bias erasure to going back to then physically updating the switch for the next measurement?
Yeah, so there are many. So yeah, that's an excellent question. That's something that we worry about quite a lot. So in the game is that we have been playing games with fiber essentially. So one of the advantages of I kept it as a backup because I knew this was going to come up. So there is actually a game where we actually there is a game called interleaving that we play, where you can actually, because of the fact that you have a photonic fiber available to you, it's possible to sort of delay photons for a long time and take advantage of that sort of situation to actually be able to switch between two measurements as well. And the second game that are described in the interleaving paper are you can actually set it up such that you don't actually have to. You can actually delay the sort of operations that I care about most in a manner which is actually helpful for this scheme. So you can play these kinds of games to actually make sure that you actually get the information when you want. So I think there is you can actually feed forward in the tens to hundreds of nanoseconds regime typically, and that sort of is something that we expect to be good enough for our particular application.
So another benefit of this static bias arrangement, as you called it, is that you can, by keeping your errors in these planes, you can use codes that have asymmetric distances, right, to x and y errors. So for the same number of qubits, you can have effectively a larger distance. Yeah, right. So with this dynamic thing, I think you don't get that, right? You're deliberately putting them in both directions. So is threshold the only thing to compare, or should you also be comparing logical error rates with a given number of qubits?
So logical error rates works out well in this case as well. So we actually had a look at that as well. I haven't talked about it in the paper because whenever I talk about logical error rate, you will have to talk about the operating point itself as well. But I think we've run some sort of sub-threshold scaling, and you find that actually, so I ran some numbers and saw that if you're operating at, let's say, 0.4% loss in this scheme, you find that you end up with dynamic bias arrangement, you end up with requiring a factor of 500 fewer sort of physical resource state generations, or you end up with 500 times less footprint than you were at that particular value of physical error rate in our particular architecture.
But in this comparison, in the static bias case, sort of rearranged the qubits.
Yes, and one more thing here is that the second game that we could play, which we haven't played here, is that if you wanted to play a game of maybe making asymmetric blocks, for instance, you could just change the heuristic to say that if I care about that, just give me blocks which are actually sort of prefer a direction over the other. That is something that could be easily incorporated into the architecture. We haven't done that yet, but these are games which you could also play in this case.
Thanks.
So in the interest of time, we should move to the next speaker, but let's thank Mihir again.
Yeah. Thank you.